All right, we're going to talk about distance and displacement in calculus. You've taken physics, you know the difference. Distance is like the total amount traveled. Distance is always positive. Could distance ever be 0? If you don't move, sure. So it could be 0. But as long as you're moving, you're going to have some distance. Displacement is just your change in your beginning position compared to your ending position. We know displacement could be positive, it could be 0, and it could be negative. Example is this red guy going to the right to 6 and then coming back down to -6. So if I start at 0, I go to the right to 6, and then I come back to the left to -6. The distance would be the +6 plus the +12 length that he traveled to the right, and then plus the 12 to the left, or 18. However, the displacement would just be the change from his ending, which is at -6, compared to the where he started at, which is at 0, and the displacement would be -6. Okay? Cool. Well, let's talk about distance and displacement in terms of in calculus. We've already talked about this. I kind of used displacement, actually I used distance to talk about areas under curves, right? Here's an example that I used kind of in class. Say if a particle has a velocity of 4 meters per second, find the distance the particle travels from 2 to 6 seconds. And we said there's 2 ways to do it. You can either do your velocity times your time. Well, you could look at that using an integral. You go from 2 to 6 seconds of your velocities times your times. We would take an infinite sum of our velocities times times. However, in this case, since velocity is just going to be 4, you know you're going to have a velocity of 4 that you're going to be traveling at for 4 seconds, meaning I have a total of 16. But the other way is using the fundamental theorem of calculus and said we can find the change in position. I could take x of 6 and subtract x of 2. So instead of doing this, I say that's going to be equal to the antiderivative. In this case, I can kind of go down a little bit and say this is the integral from 2 to 6 of 4 dt. We already know that's 4 times 4, which is 16. But the other way we could do it is find the change in the antiderivative, which would be 4 times 6 minus 4 times 2. That's 24 minus 8. That also gets you 16. Okay? And that's how I introduced you to the fundamental theorem of calculus. That to find area under a curve, which is essentially just function values times infinitely skinny widths, instead of worrying about that, just find the change in the antiderivative. The connection being distance can be velocities times time, and distance can be the change in position. Well, I was incorrect in my explanation. Okay? I was wrong. When I was teaching you the fundamental theorem of calculus, I was saying distance is your change in your position, or your velocity times time. What should I have been saying? Displacement is the change in your position. Displacement is all of your velocities times time. Okay? So go back to the fundamental theorem of calculus lesson and change your brain from me saying distance is velocity times time to displacement is an infinite amount of velocity times time. Instead of changing your position being distance, really changing position is displacement. Here's an example that might help clear things up with what I was just mentioning. If a particle has a velocity of negative 2t plus 4 meters per second, find the distance the particle travels from 0 to 4 seconds. And the initial position part does not matter. Well, I could take an infinite sum of my velocities times times, but let's just go ahead and use the fundamental theorem of calculus and say this is going to be equal to the change in my position between 0 and 4. I'll get negative 16 plus 16 minus negative 0 plus 0, and I get 0. Okay? Did I answer the question? Is the distance of this particle with a velocity of negative 2t plus 4 going to be 0? No, right? Because the distance is always positive. Distance is only 0 when what, Mr. Mayor? We don't move. Are we moving? Yes, we have velocity. It's not going to be 0 all the time. So we are moving. We are finding distance, or we want to find distance. We should have a positive value, but here, if I did what I was doing previously, which is velocity times times, or change in position, I get 0. This is the wrong answer because this, what I have found, is actually the displacement. Okay, well, that clears some things up, but I still don't know how to calculate distance right now. Well, the way we're going to calculate distance is we're going to first look at this situation graphically. Okay? And I said, okay, well, the displacement turns out is going to be the infinite sum of my velocities times time. Well, let's figure out how I can get 0 graphically. I can just look at the areas under the curve of negative 2t plus 4, the same as taking your infinite velocities and multiplying by times, and I could sum them together. So I got the triangle, length 2, height 4. This is a triangle of area 4. And then I have this triangle of area, length 2, height negative 4. This is going to be negative 4. That gives me that displacement of 0. I am traveling to the right when my velocity is positive. I'm traveling to the left when my velocity is negative. Who can tell me what my distance is going to be? 8 is correct. 8 is correct. This right here between negative 2 and 0 is going to be a positive displacement. I travel a total of 4 units to the right. This right here is going to be a negative. I don't know why I said negative 2 to 0, from 0 to 2. This from 2 to 4 is going to be a negative displacement. Or I travel to the left a total of 4 units. Well, all I need to do is take my positive displacements, keep them positive, and then take my negative displacements and make them positive. And I get my correct distance, which is 8. What did I use? I use a absolute value, as I heard some people say, where I take positive things, keep them positive. I take negative things, I turn them into a positive. Boom. Using that absolute value, we will get the correct answer. Now, what is that going to look like in terms of an integral? Well, displacement we know is just going to be the area under my velocity curve. It's my infinite velocities times times. Velocities could be positive or negative. Turns out this can also be displayed as the change in my position. Well, that is just the definition of displacement. So that means my area under my velocity is displacement. Well, distance, I want to take the absolute value of all of my displacements. So I need to take the absolute value of all my velocities times time. Well, I could do this. I could say, okay, take the absolute value of all of my velocities times my times. But one of these things I know is always going to be a certain type of value. What do I know is always going to be a certain value? dt, the change in time, is always positive if we're going from left to right. dt is going to be positive, therefore I can make this look like this. And all I need to do is take the absolute value of my velocities, multiply them by my times, that becomes positive displacements. Okay? This is positive displacements, taking your velocity times times and making sure they're positive. This is also positive displacements. Okay? This is distance. Okay? Now, I could give you a question like this. I ask you to find the distance of a particle whose velocity is t minus 3 from 2 to 5 seconds. And if I let you use a calculator, you'd say, piece of cake, Mr. Messner. Let me just plug this into my calculator. Everybody plug that into your calculator and see what you get. Let's recall how to pull up the absolute value symbols. You need to go to math and then over to number, and you see abs. Abs stand for absolute value. So I'd go math 9 from 2 till 5 of math number abs t minus 3 dt. Well, this is interesting. Your calculator gives you 2.500005956. Does that mean the answer is 2.500005956? Answer is probably going to be 2.5, right? Why do I say that? What is my calculator doing? It's approximating using a lot of Riemann sums, right? A large Riemann sum. Well, we know Riemann sums sometimes miss little bits of area or sometimes overestimate areas. In this case, your calculator using a Riemann sum actually overestimates the area. You can go ahead and assume that the area under the absolute value of t minus 3 is 2.5, and this is going to be the distance. Okay, piece of cake. Well, what if I asked you to do this question without a calculator? Makes it harder, right? If I just wrote this down like this, and I wanted to use maybe the fundamental theorem of calculus, what do I have to do to find this? Find the antiderivative of the absolute value of t minus 3. Have we talked about antiderivatives of absolute values yet? Are we going to talk about antiderivatives of absolute values? No, we're not. They're just different. They're more complicated because things change in terms of its signs depending on where you are. So Here we're going to have to think of another way. Maybe we're going to graph. Let's look at some examples graphically. And maybe if we understand how to find distance graphically, we can understand what to do without a calculator for that previous question. Top of the D went away. Okay, remember my previous example. I had this positive displacement, which was positive 4. But then what did I do with this negative displacement? I took the absolute value and I added it, right? Well, what's another way to do it without using an absolute value? I heard the S word. Yeah, why don't we subtract this negative area from 2 to 4? All of a sudden, I have my positive displacement of 4 minus my negative displacement of negative 4. That gives me all positive displacements, I get 8. That's the idea on how we're going to do these problems without a calculator. We need to figure out when my velocities are positive. We need to figure out when my velocities are negative. When I have positive velocities, I'll have positive displacements. I'll just add up my positive displacements. When I have negative velocities, I'll have negative displacements. I'll need to subtract those negative displacements. And what I will be doing is essentially taking the absolute value of all of my displacements and adding them together. So you guys write, using integrals, how I'd find the distance of a particle between 0 and 4 if the velocity follows this curve. Check your answers. Oh, excuse me. Check your answers with the neighbor. Just write all the integrals. I don't know what the areas are. Just write the integrals at least. We don't know what the answer is going to be numerically, but we can write all the integrals down. I'm going to be moving to the right, then moving to the left, then moving to the right. If I just summed up all of those areas, I would get my total displacement. So the difference between where I started and where I finished. But if I wanted to figure out how far I've traveled total, I would need to take my positive displacement between 0 and 1. Subtract my negative displacement, which will be just adding a positive displacement between 1 and 3. And then I will add my final positive displacement between 3 and 4. And if we can understand that, we're good for this lesson. Okay? Now let's go back and see if we can do that with this guy. Now last class, I didn't get through all the work. Let's do it in this class. Without a calculator, here's what we're going to have to do. And we can write this down. Examine the signs of velocity. When I want to figure out when velocity is positive and negative for a given velocity function, what's the first thing I should do? I want to figure out the signs of something. What's the first thing I should do? Find when it's 0. Find when it's equal to 0. Add all of your positive displacements when v of t is positive. Subtract the negative displacements when v of t is negative. Okay, let's see how that would look here. First thing I would do, I would take my velocity function, set it equal to 0. T minus 3, keep saying equals, t minus 3 equals 0. That means t is going to equal 3. That's when velocity is positive. Second thing I'm going to do is examine the signs of my velocity around that 0. Well, I know when t is greater than 3, my velocities are going to be positive. When t is less than 3, my velocities are going to be negative. Go ahead and write your integrals after that. Since my velocities are negatives, the area from 2 to 3 is going to be negative. I will have to subtract that area from 2 to 3. And then I know the area from 3 to 5 is going to be positive because my velocities are positive. I will add the area from 3 to 5. Now, typically, you'll be able to leave your answer like this. Because what you'll find is that the grunt work of doing this without a calculator is pretty nasty. Let me show you why. We'd have to take the opposite of 1/2 t squared minus 3t change between 2 and 3. Then we'd have to add the change in 1/2 t squared minus 3t between 3 and 5. So I'd have to do all of these calculations. I'd have to do the opposite of 9/2 minus 9 minus the quantity of 2 minus 6 plus 25/2 minus 15 minus the quantity of 9/2 minus 9. And as we can tell, like, I don't want to do that. Okay? We will be able to stop here for most questions. For most questions. For this question, I might ask you to actually find the value, which means you'd have to do this. Or, there's another way. What would be the other way? Let's put our phones away, Ms. Crusade. Thank you. What's the other way, Ms. Klein? Okay, well, let's answer your question first. Yeah, because I purposely cannot take the antiderivative of that. That's the whole thing. I can't find it unless I had a calculator. So, like, yes, theoretically, this is correct. This is correct. However, in practice, if we don't have a calculator, we're going to have to look at doing this. Adding our positive displacement, subtracting our negative. We got that? Okay. Now, for this problem, this, using the fundamental theorem of calculus, is tough and stinks. What is an easier way to do that? No, without our calculator. Graph it. T minus 3 is a straight line. Let's see if we can graph t minus 3 between 2 and 5. Yoink, yoink. 1, 2, negative 1, 3, 0, 4, 1, 5, 2. This is the graph of t minus 3. I can simply just take this area. What's this area going to be? This is at negative 1. That'll be negative a half. And then this area, 1, 2, height of 2. What is this area going to be? 2. What is my distance? 2.5. Right? Because this is a negative displacement. This is a positive displacement. 2 plus positive a half. Or you could say it's minus the negative a half plus 2. Or 2 minus the negative a half. That gives you the 2.5 that we were looking for. If I did this in a calculator, I'm going to do it. Because I don't want to do it by hand. The opposite of 9 halves minus 9 minus the quantity 2 minus 6, closed quantity again, plus the quantity of 25 halves minus 15 minus the quantity of 9 halves minus 9. Close that. Close it again. 2.5. Right? So we could have done that way. Here's a problem you might see. The particle has a velocity of t squared minus 7t plus 10. Just write the integral expressions for the distance and the displacement of the particle between 1 and 7 seconds without using an absolute value. I'll do displacement, you guys do distance. The integral expression for the displacement would just be the integral from 1 to 7 of t squared minus 7t plus 10 dt. If I let you use an absolute value, your answer would be easy. It would be the integral from 1 to 7 of the absolute value of t squared minus 7t plus 10 dt. But I want you to write the integral expression or expressions without using an absolute value. So give me another answer for that. Go. Step 1, examine the signs of your velocities. How to do that? Find when velocity is equal to 0, and then examine your signs around those. Step 2, when you have positive velocities, you would have positive displacements. You're traveling to the right. Add up those positive displacements. If you have negative velocities, you are traveling to the left. You'd have a negative displacement. Subtract those negative displacements to make them positive. Everybody can do this. Give it a shot. Don't just stare at it. I don't want you to get an answer. Just write the integrals. Check your answer with a neighbor. Ms. Keith, you need to find when the velocity equals 0 first, just like we set up here. Did we write this down? Did we write this down? Okay. Find when the velocity equals 0 first. When the velocity is positive, add those displacements. When the velocity is negative, subtract those displacements. Everybody can do this. Don't just stare at it. Simple factoring of my velocity function shows me that my velocity is equal to 0 at 2 and 5. Going from there, we can examine the signs of my velocity using the factored form of t minus 5 times t minus 2, saying my velocity is going to be positive when t is greater than 5, negative between 2 and 5, and positive to the left of 2. Questions? Okay, now that I have that, I know this is when I'm moving to the right, I'm going to have a positive displacement. This is when I'm going to be moving to the left. That means I'll have a negative displacement. This is when I'm moving to the right, positive displacement. Add your positive displacements. 1 to 2, 5 to 7, subtract your negative displacement from 2 to 5. Doesn't matter which order you put things in. You can go 1 to 2 plus 5 to 7 minus 2 to 5, or you can just simply go in order of your velocities. 1 to 2 minus 2 to 5 plus 5 to 7. Not hard. Everybody can do it. Okay? Now, using a calculator, go ahead and find this actual displacement and this actual distance. Just for fun. Going from 1 to 7. 1 to 7. See your calculator working. Takes a while to deal with all these absolute values. An extra step in its calculations. Okay? That's the easy thing. You won't have to do that much on the AP exam. You might have to do this a couple times. You might have to just recognize that this stands for the velocity of something. I mean, the distance of something. Okay? Any questions?
Do you use this with like other things other than velocity?
Nope. Typically, we will not want to take negative function values and make them positive. Unless we want, no, I can't even think of anything. I can't even think of anything. So, always V of t in this absolute value. Now, let's be careful, because on our quizzes and on the tests, usually we just start doing something and we just like do it for every single problem. We don't read the question carefully. This is an example of how if you don't read the question carefully, you're going to get the question wrong. Let's read this question carefully and see if we can figure this out. I want everybody to do this. At least attempt it. If you need help, ask a neighbor or ask me. But everybody's working on this question, and this is the last question we have. You're allowed to use your calculator, by the way. But if you have time, write down your integrals without an absolute value. This middle part here is what we need to do first. Because we know the displacement is the infinite sum of my velocities times my times. I need velocity. We know distance, infinite sum of my positive displacements. I need velocity. I'm given acceleration. I need to take the antiderivative and find the velocity. That is step one. We find that the velocity function is 2t squared minus 8. Once we have that, the rest is just plugging it into your calculator. From 0 to 3 of 2t squared minus 8 will be the displacement. From 0 to 3 of the absolute value of 2t squared minus 8, that would be the distance. If you want to go a step further and write your integrals without an absolute value, which you will be asked to do, you need to examine your signs of your velocity, set your velocity equal to 0, figure out t is going to be equal to plus or minus 2 to make this true. That means your velocity is going to be negative between -2 and 0. I mean, from -2 and 2. That means we'll take the opposite of my negative displacement from 0 to 2 and add my positive displacement from 2 to 3. That will be my integral expression without an absolute value of the distance traveled. Any questions? We get -6 for my displacement and 15 1/3 for my distance. And if I plug this in, I'd get 15 1/3 as well. Your homework's a worksheet. I have the worksheet. Back there. Thank you.